Using regression analysis for forecasting, Chapter 8, Sections 8.4 through 8.5. Linear trend. Now, a linear trend is something we've already covered under linear regression. It's the same idea. It's exactly the same concept as we've covered before. And now we're just applying exactly the same concept to forecasting. So pretty much what we're saying is that if we have a set of data, draw it on here. If we have a set of data points, we can actually fit the best fit straight line through that data historically, and then we can actually project or forecast into the future. Okay, that we can project down here, and this is the part of linear forecasting. So that's all we're doing here. A couple of things to just know is about regression analysis. Regression analysis is for linear trend is fairly similar. Let's see that we have a trend variable. That's new terminology. The trend variable is the time period, because typically our variable here on this axis is in fact going to be time, and the other variable on the axis up here is going to be it could be anything. It could be demand, it could be sales, it could be anything we want. But on this axis here, it's going to be time on the x-axis. So y, it's got the same meaning as it had before. It's basically the dependent variable, and the hat on top means it's like the estimated or the predicted value for y. B0 is the intercept, B1 is the slope, and t is just the time. And before we had x corresponding to the x-axis, but now on the x-axis we're just going to have time. So let's see an example. Let's go back to the data for this example. As you can see here, this is the bicycle size sales data, for example, and here's the actual data for it. So what we like to do here is try and forecast what's going to happen in period 11. So we've got the first 10 years of actual data. We'd like to forecast what's going to happen here in period 11. We'd like to forecast this value. So let's put forecast in here. So how do you actually do that with a time series? Well, one way of doing that with a time series is to come up with the actual regression line. So what we can do, let's actually see what the regression line looks like. Insert. And this time, rather than do a scatter plot, I'm going to do a line chart with markers. And there you go, that's what it looks like. So generally speaking, the trend is upwards for the bicycle sales. And that seems the same as we had before. It seems reasonable to use a straight line to model this data. It's not exactly falling on a straight line, but a straight line may not be too bad a fit for that data. We could also have done the scatter plot for it. Let's see what the scatter plot looks like. Insert and go for scatter plot. And that's what the scatter plot looks like. So you can see that a straight line may fit through that data fairly well. Now, how can we actually do that? There's the quick way of doing it. If you remember, the quick way of doing it is to right-click on any of these data points. So let me just come out. Right-click on any of these data points and go to add a trend line, and automatically Excel will fit the best fit straight line through that data. There's other options, but it defaults to linear. And we can do a bit of time saving, have a bit of time saving here by pressing display equation to chart, and also down here display R squared, and you can see we're actually getting those in one fell swoop. We can close this off, and there you go. Close this one as well. Just delete that. So that's one way of doing it. Another way of doing it to actually get the regression equation is just to use data analysis. So we can go to data up the top here, and then data analysis over here. Go to regression, press OK, and input our data. So our X range and our Y range. Now, in this case, sales would be the dependent variable because sales are the ones that change over time. So sales will be dependent on time, and I already put the data in there, as you can see. I've clicked on labels because I included labels. If I include B1 and A1 in my ranges, then I have to click on labels because A1 and B1 are both labels. And let's put the output in cell D1 here and see what the output looks like. That's the output. And what we're really interested in for the regression equation is a couple of things. The first thing is the value of R squared, 76%, which happens to be exactly the same as the value we got over here. And so we know that the model is fairly good for R squared. R squared, remember, is a value between 0 and 1. The closer it is to 1, the better the model. The closer it is to 0, the worse the model is. And the intercept and the slope. Now, I already knew what the intercept and the slope were because they were 20.4 and 1.1. So we see it from up here. So what does that actually mean for us in terms of forecasting? So what it means for us is we have an equation. Our linear regression equation is going to be y hat equals b0 plus b1. You could call it x, but we're calling it t now. And what is the hat? That means the estimated. And y, so y cells, so estimated cells of bicycles equals the intercept, which is 20.4, plus the slope, which is 1.1, times whatever time period you're in. And we're using time as years. So now we can work things out. So if I want to work out the estimated cells here for year 11, all I have to do is actually cross that out and put an 11 in here. That's all I have to do. And what's the answer going to be? Let's come over here and do the actual calculation. Let's come out of this. Let's do the actual calculation here. It's going to be equal to the 20.4 plus the slope times, you can multiply it by t, that's year you're in, which is 11. And there you go. So it's going to be 32.5. So our forecast is going to be 32.5 bicycles. Other interesting information from here is that 1.1, the slope, basically tells us that over the past 10 years, we've got data for 10 years. For the past 10 years, the slope is 1.1, and it's in thousands, so it's 1,100. But over the past 10 years, the firm has experienced an average, so the average over the 10 years, growth in sales of about 1,100 units per year. That's what this slope in here means. And it means for each additional year, on average, our sales are going to increase by 1,100. There's another little quick way that you can actually do some of this stuff actually when you want to fit the best fit regression line. I'm going to copy this and I'm going to just bring it to here. Just paste it in here. So there's a little trick that you can do, which you can highlight this and you can actually drag down. And you can see that actually filled it in for us. And I can keep on dragging down. And Excel knows to actually put the forecast moving forward for you. This will only work for linear regression, and it will only work for linear regression time series analysis, where your time periods are in sequential order, 1, 2, 3, 4, 5, etc. Otherwise, it will not work. So let's go back to the PowerPoints. And this is the equation that we get, and again, the example we just did about in year 11, what's our forecast going to be? Moving on. Using regression analysis for forecasting, again, we're continuing with more complex models. So this is a more complex model. It looks similar to a multiple regression model, apart from the fact that we have these powers, these squares and these cubes. If we were to cut out t squared and t cubed, this would look like a multiple linear regression model. But right now, it's not a multiple linear, it's a more complicated model. But we can use models as complicated as we want. There's not always benefit from making a model more complicated. We're trying to predict the future, and we don't really know what's going to happen in the future. So overcomplicating a model may not be a wise idea. Autoregressive models down here are models where the independent variables are based on previous values of the time series. So the model kind of feeds itself. You look at the past data and you use that past data again to predict with what's going on in the future. Now we can have a look at seasonality without trend. Do you remember what seasonality was? Seasonality is a recurring pattern over 1 year or less. And we had an example that we looked at before, which was the example with the umbrellas. And if we have a quick look at that again, here it is. I'm going to just quickly plot this so we could see it. So it gives a reminder. So I'm going to do insert, and I'm going to go for a line with markers, and that's what it looks like. And this was the seasonality. And if you remember, I said season 1 and 3 are moderate, season 2 is high, and season 4 is low. And that pattern repeats itself each year. So 1 and 3 moderate, 2 high, 4 low. 1 and 2 moderate, 2 high, 3 low. 1 and 3 moderate, 2 high, 3 low. And then you can see it again. 1 and 3 moderate, 2 high, 3 low. So we do have a seasonal pattern. Now, seasonality is a categorical concept. It's not going to be an actual number that we're going to be looking at. So how do we account for seasonality? If you remember, we're going to be using a dummy variable. And the way the dummy variables works is you find out how many categories K your seasons have, and in this case it's 4, and the number of dummy variables we need to introduce is going to be K minus 1, which is going to be 3 dummy variables. So that's what we're going to do, and you can introduce the dummy variables in different ways. Here's what the PowerPoints are suggesting. So let's have 3 dummy variables. One is going to be called Q1. Let's just call it Q1 rather than quarter 1, but quarter 1, quarter 2, and quarter 3. So quarter 1, that variable will equal 1 if we're in the first quarter, and 0 otherwise. So 0 otherwise means 0 for everything else, not just quarter 1, but 0 for everything else. Quarter 2, Q2 will take a 1 if we're in quarter 2, 0 otherwise, and likewise quarter 3 will take a 1 if we're in quarter 3, and it will take the value of 0 otherwise. So what about quarter 4? Remember, there's always a default category. If I'm not in quarter 1, if I put a 0 for quarter 1 and I'm not in quarter 2, put a 0 for quarter 2 and I'm not in quarter 3. So if all these 3 quarters are 0, by default I must be in quarter 4. So let's go over to the actual PowerPoint and run this and see what we're going to get for it. And note what our regression equation is going to look like. Y equals the intercept plus like 3 kind of slopes with Q1, Q2, and Q3. So let's have a look what that's going to look like for us. So I'm going to have to introduce 3 dummy variables, Q1, and then Q2, and then Q3. And so remember, it said if I'm in quarter 1, I'm going to put a 1 for quarter 1, and a 0 for quarter 2, and a 0 for quarter 3. And if I'm in quarter 2, by the way, and I'm in quarter 1 up here because it says quarter 1. And down here, I'm in quarter 2. So if I'm in quarter 2, I am not in quarter 1. I am, yes, in quarter 2. I am not in quarter 3. And for quarter 3, I'm not in quarter 1. I'm not in quarter 2. I am in quarter 3. And quarter 4, I'm not in quarter 1. I'm not in quarter 2. I'm not in quarter 3. So therefore, by default, I'm in quarter 4. So that's how you do that. That's how you introduce the dummy variables. And what I'm going to do is I'm going to copy that down to here, so that's just going to repeat itself. I'm just going to repeat the dummy variables because you can see that when we go to year 2, we're in quarter 1, 2, 3, and 4, and then year 3 is quarter 1, 2, 3, and 4, and so that pattern repeats itself. And to just run this is nice and easy. We're going to run a regression on it, the regression that we're used to. So we're going to hit data up here and data analysis over here and regression again. Now our dependent variable in this case is what? Our dependent variable is our sales. And if you look, I input the data, D1 is included in my Y data, and that means I'm going to have to click on labels. And then my X range, I put all these 3 in one block. So that's what this is in here, all 3 of them in one block. I have included labels, so I've clicked on labels. Let the output go to I1. Where's I1? Right there, that's okay. Let's press OK. And we get our answers. And this is what we're going to focus on in here. So we can predict the umbrella sales now in whichever quarter we happen to be in. R squared is nearly 80%, which is good. It's telling us how, giving us a rating, if you like, of how well the quarters are predicting your sales, and that's pretty good. And so remember, our regression equation from the previous page had the form. It had the form y hat equals b0 plus b1 times t plus b2. Actually, it was q, wasn't it? It's q1 b2 times q2 plus b3 times Q3. There you go. So it's a bit confusing. We're normally using x1, x2, and x3, and now we've changed to time, but we've put dummy variables in as Q. So anyway, these are Q's, are the dummy variables. Doesn't really make any difference. You just have to keep track of what you're doing. So that little hat means the estimated, and Y we actually said is going to be the cells. So the estimated cells are equal to B0. Now B0 is 95. 95 plus B1, which is 29, times Q1. And remember, Q1 is 1 if you're in the first quarter and it's 0 otherwise, plus, what's that number in there? 57 times Q2, plus the last one is 26 times Q3. So this is how I work anything I want to work out for the estimated cells. Interestingly enough, if I happen to be in quarter 4, what does that mean? When I'm in quarter 4, then some of the values go to 0. This will go to 0, this will go to 0, and this will go to 0. So if I'm in quarter 4, my estimated cells are just going to be 95. How about if I am, say, for example, in quarter 1? What will my estimated cells be? Well, if I'm in that quarter, the only thing that is actually going to disappear, if I'm in quarter 1, this is going to be 0, and this is going to be 0, but this is actually going to come back in. So Q1 will be back in, so that's going to take the value of 1 in here. So what's the value going to be? So your estimated cells, if you're in quarter 2, are going to be 95. Let me do it over here. So it's going to be 95 plus 29. So it's going to be 95 plus 29. So that's what your cells are going to be. So the way this basically works, it's taking, it's actually taking quarter 4 as like your base quarter of 95. Your cells are 95. And for quarter 1, it says how much you have to add to quarter 4 to get to quarter 1. And 57 is telling you how much you have to add to the 95 to quarter 4 to get to the quarter 2 figures. And likewise, the 26 is saying if I use quarter 4 as my base of 95, I have to add 26 to the 95 to find out what the cells are going to be for quarter 3. So that's just simply how it works. And by the way, this would actually equal 124. So that's your quarter 1 cells are going to be 124. And you can try this as an exercise on your own. What will the quarter 2 cells be? Well, the quarter 2 cells would be, well, this guy's in here is going to be 1, this is going to be 0, and this is going to be 0. So your quarter 2 cells should be 95 plus 57. Okay, and 95 plus 57 are going to equal to 152. So you can just work that out by yourself. That's how easy it works. Let's go back to here. Moving on, let's have a look at the actual output that we had in Excel. Let's do another example now. This example we're going to do next is on the smartphone. And the smartphone, if you remember, was an example where we had both seasonality and trend. So let's go over to that data again, which we've already seen before. Let's just remind ourselves. And let's just insert a line chart with markers. And there you go. So here we can see not only do we have an upward trend, we have a repeated pattern recurring in a year. As long as it's a year or less, then that's going to come under seasonality. So let's move that to the side. How would we deal with that? Well, we've got 4 quarters or 4 seasons. And seasons are categorical variable. And the way we deal with categorical variables is to put in a dummy variable. How many dummy variables do we need when we've got 4 levels? Well, it's going to be 3. K is the number of seasons or levels that you've got, and we've got the way we find the number of dummy variables we need for the categorical variables is going to be K minus 1. 4 minus 1 is just going to be 3. And we're going to just, again, we can use Q1, and we can use Q2 and Q3. So this takes account of the seasonality, but we also want that trend. When the trend happens over time, so I'm going to put a T in there for the trend. So if I am in quarter 1, I'm going to put a 1 in here, and I'm not in quarter 2, I'm not in quarter 3, and it's time period 1. How about when I'm in quarter 2? Well, I'm not in quarter 1. Yes, I am in quarter 2. No, I'm not in quarter 3. I'm in time period 2. How about for quarter 3? Well, in quarter 3, I'm not in 1. I'm not in 2. Yes, I am in 3. And that's period 3. And finally, when I'm in quarter 4, I am not in 1. I am not in 2. I am not in 3. And by default, I'm in 4. And that's the times for that's going to be time period 4. I'm going to just repeat these. I'm going to copy these. And I'm just going to repeat these down to here. And I just want to go 1, 2, 3, 4 and continue it going down. And Excel's fairly smart. It's going to pick up this sequence. Just do that. It's going to pick up this sequence when I just use my mouse. It's going to pick up the sequence in those numbers and finishes off for us. And how do we actually go on to actually get the numbers? Now the numbers or coefficients I'm referring to are the coefficients we're going to put into this equation. So here it's telling us the equation looks very similar to the one we had before, and where it was when we just had seasonality. But now we've got trend. What the difference is that we're just going to add this bit to the end. So this was the same as the one we did in the previous example on the umbrellas. Now we're adding in trend. We've just got this additional piece on the end. And let's go back and just put that through regression. So we're going to hit data up the top, data analysis, regression, and what we're going to put in my Y range is going to be my dependent variable, which is the cells in there. And my X range is going to be all of those guys in there, Q1, Q2, Q3, and T. And I will click on labels, and I'm going to put the output into cell H1 there, press OK, and that's the output. And is this model any good? Yep, it's not bad. Look at that. That's pretty excellent. When we look at the value of R squared, 97%. If you remember the scale from 0 to 1 for R squared, 1 or 100% means that model's pretty good, very, very good. And we're at 97%. So the model's excellent. And I can just actually finish off the model by putting these values into here. So what I can do is just draw it out here. So what we can do is we could say that, let's get one of the colors, bit in black. So we could say that y hat, the estimated value of y, which is going to be the estimated cells, is equal to B0, and B0 is 6. And just for ease, I'm just going to put 6.07. Okay, I've just rounded that figure up, 6.068. I've just rounded it, and then I'm going to add in B1 Q1. So B1 is going to be, oh, it's not a plus, it's in fact a minus. So that's interesting, that's a minus. Let's just get rid of that. Just move that mouse out of the way. And so let's see, go back to putting it in. So it's going to be minus. And I'm going to put 1.4, it's 1.36. I'll just put negative 1.4 times Q1. Remember, Q1 is 1 if we're in quarter 1, is 0 if we're not. And then we're going to put in the next one. Oh, again, that's another negative one. So it's be negative 2.03 or 2.0 to 1 or 2 decimal places. Let's put in 2.03. And that's going to be multiplied by Q2. Remember, Q2 equals 1 if you're in period 2 or quarter 2. Otherwise, it's 0. And then the next one is also negative, which is going to be, let me come down. It's going to be negative 0.3 times Q3. And then the last one is going to be plus 0. Let's say 15. This guy's 0.15 times the time period that you're in. So that's how you work out your estimated cells. And just to complete this as well, it's going to be B2 Q2 plus B3 Q3 plus T. So that's the actual equation. I can work anything out I want to now. So what's interesting about this is that when you're in Q4, Q4 is your base. And what I mean by that if I put Q1, Q2, and Q3 all equal to 0, if I put this, this, and this equal to 0, that refers when I references quarter 4. And what actually happens when when I say, okay, quarter 4 is my base, and then Q1, to actually find the figure for Q1, I have to subtract from Q4, I have to subtract 1.4. And to get to quarter 2 from quarter 4, your base, I have to subtract again, and also for quarter 3. So that means that quarter 4 has the highest values, because all the other quarters, to actually find them from your base of quarter 3, from quarter 4, you have to subtract from them. So quarter 4 is the base to get to quarter 1 or to quarter 2 or Q3. You can see that all the coefficients are negative, so I have to subtract to actually get to them, which is fair enough. There's not a problem. And if we want to find out what the sales are going to be in a particular quarter, so if it's, say, for example, quarter 2, we're going to put this guy in here equal to 1, and this equal to 0, and this equal to 0. And it's good that you have to not only say which quarter you're in, but you also have to say which time period you're in now as well. So if I'm going to be in year 5, let's put it in here. If I'm going to be in year 5, quarter 1, so I'm going to have to tell it the quarter that I'm in is the first quarter, and I'm going to tell it that by putting Q1 equal to 1 and the other guys equal to 0. And I'm going to tell it that I'm in period 5, year 5, sorry, but what period will that be? That will be period 17. So if I wanted to actually calculate the forecast for year 5, quarter 1, which is going to be the next thing in line. We've got the data for all the previous stuff. So now I want to forecast forwards for year 5, quarter 1. How do I do it? Well, it's going to be equal to 6.07. I got that from here. And quarter 1 is going to be minus 1.4 times 1, because we're in quarter 1. And then minus 2.03 times 0, because I'm not in quarter 2. Minus 0.3 times 0, because I'm not in quarter 3, I'm in quarter 1. And then I'm going to have to add in 0.15, and the t I'm going to have to put in is 17, because that corresponds to period 17. So I have to multiply that. I have to multiply this figure here by 17. So that's how you would do that. Let's just quickly go back to the PowerPoints and see what else they're giving us. That's the actual data that we have on the previous sheet, and this is just explaining to you just a little exercise similar to what I just did right now. If you're in quarter 1 or quarter 2 or quarter 3, this is how you calculate everything. So you can actually try that yourself. When we said for quarter 1 sales, it's just putting the quarter 1. This is referring to the quarter 1 of any year. So the quarter 1 of any year, and by any year, they haven't actually put a value in for this t in here. So t is going to be the time period that you're in to complete that. So if you're in quarter 1 of year 5, which is the example that I just did, this is quarter 1, but if it's year 5, you're going to have to put in a number 17 in for t. Just remind us why that is, because quarter 1, year 5, quarter 1 of year 5 is going to be right there. It's going to be 17. So 1, 2, 3, 4, 15, 16. It's actually going to be 17. So that all makes sense. Try that yourself to make sure that you can get those values out. Causal model. So you may have heard of cause and effect. And what is a causal model? Well, all this refers to is does your model, is it a causal model or not? When we did the example way back when, and I'll do that example again on the a student, and we said that we got the student, and this student studies for an exam. Do it here, and this is the hours they study. This is the hours they study, and hours they study, and this is their exam score. And we find some relationship which hopefully is increasing as you study more hours, you get a higher score. So it's fairly obvious, using practical experience that the amount of hours you study actually causes your exam score to go up. And if you study fewer hours, it causes your exam score to go down. So it's fairly obvious that these two variables are correlated, and one is actually hours is causing an effect on your exam score. Now, mathematically, we can find relationships between two variables where they're not causing the effect. You say, how can that be? Well, let me give you some examples. Did you know that the consumption of mozzarella cheese in the US is actually correlated to the amount of civil engineering doctorates that are given out? So if I was to have consumption of the cheese consumption here and PhDs to engineering students, I know that statistically there's a relationship, but practically, using my experience, I know that's not the case. On the previous example, I know if I study more hours, I expect my exam score to go up. Down here, though, if I eat more cheese, I don't expect more people to get PhDs in engineering. So sometimes there are statistical relationships. It's a real statistical relationship, but it's just spurious. It's just a random relationship. A causal model is not based on random relationships like this. A causal model is going to be one like this, where you know based on your practical experience that one of the variables is impacting or causing the effect in the other one. So that's all the causal model is. A causal model is that we include variables only that we believe, by practical experience, change the variable to be forecast. It's interesting, I'll give you a couple more examples of models that are not causal. I would not assume a causal. The divorce rate in Maine is correlated to the consumption of margarine. Again, if you eat more and more margarine, you don't expect more people to be getting a divorce in Maine. And another one is where there's a statistical relationship, but the effect is not a causal effect. So there is a statistical relationship between the amount of movies that Nicolas Cage, the actor, makes, or has appeared in rather, and the number of drownings in swimming pools. So even though that is statistically correct, and you can prove it statistically, we know being practical people and using common sense that the guy has nothing to do with people drowning in swimming pools. So a causal model is where you only leave items or variables in your model that actually cause the effect, and you would not, in a causal model, you would not look at things like cheese causing an increase in the number of PhDs, because even though it's statistically correct, it's actually practically and logically not a good idea to include it in your model. So let's move on to the next example. This is an example about somebody who owns 10 restaurants, and they've recorded for each restaurant the quarterly sales in thousands of dollars, and also the student population near the restaurants. In fact, this information resides in this spreadsheet over here. So presumably they want to see if there's a relationship between the sales and the student population. If there is, you would assume that the sales would be dependent, the Y variable, on the student population in the area. Why don't we just plot that to see if it looks as if there is a relationship between them? So let's go for a scatter plot this time. And yeah, it does. It seems that as the student population increases, the quarterly sales also increase. And we can do the little cheat thing, which is right click on this blue point, any one of these blue points, add a trend line, and that gives us the best fit straight line through the data. We can always come down to the bottom right as well, display equation on chart, display R squared, and that actually gives us a lot of information. We could have also got that information for R squared being 90% and the intercept being 60 and the slope being 6 by using data analysis. So if we go over to data here at the top and over to the right on data analysis, go to regression, and we can input our data for my Y range is this, my X range is going to be this. I'm going to include labels, so we include it in the range. Let's put the output in cell D1. D1 makes sense. Okay, let's go for that. And that does indeed give us what we were expecting to see. The R squared is 90%, exactly the same as it says up here. And the intercept and the slope are 60 and 5 respectively, as it tells us up here. By the way, I'll just tell you now, adjusted R squared, which is below R squared, it's another measure that says when you only have a small amount of data points, your R squared tends to overestimate how good your regression is. And so when you only have a few data points, you really should look at the adjusted R squared, because it says, look, you don't have a lot of data points, so you should look at the adjusted R squared. Here, even though we've only got 10 data points, there's not too much difference between R squared and adjusted R squared, because the adjusted R squared is adjusted down. And if we had more and more points, the adjusted R squared would get closer and closer to the actual R squared. We're not actually dealing with adjusted R squared. I just put that in as a side note. So what is the regression equation now for this restaurant chain? So we can actually write that in and put down what it is, and we can actually make a calculation. So we can actually say that, let's put it here, it's going to be y hat. That's going to be the estimated value of y. And what is the estimated value of y? That's going to be the estimated, and what was y? Sales, quarterly sales. And so and what are they going to actually be equal to? The estimated quarterly sales are going to be equal to B0, the intercept, plus B1, X1. And then that's just going to be equal, the intercept is just going to be 60 in this case, and the slope is going to be 5. And what is X? We said that X is the student population, so that's going to be multiplied by, let's just put ST for students, or let's TU for students. So that's the regression equation right there that we can actually use to work out any problems we have. So what else does that tell us? That tells us that, well, if we actually had no students in an area, 0 students, it would tell us that the estimated sales would be equal to 60, which basically this thing here goes to 0, and the estimated sales would just be 60 or 60,000 since it's recorded in thousands. So the students do appear, according to this model, to be actually adding to the quarterly sales. What does the slope mean? 5. That means for each additional student, your estimated sales are going to increase by 5. Because everything's in thousands, you could say for each additional 1,000 students, the estimated sales are going to increase by $5,000. So that's pretty much it for that example. And we'll just move back here. This is the graph that we came up with, and this is the regression line that we came up with in the Excel spreadsheet. Okay, so using regression analysis for forecasting, what can we say about it? Well, it's pretty flexible, it's pretty good, it's very flexible indeed, and we can actually incorporate everything we want into these models. We can incorporate trends, seasonality, causal effects. We can actually combine it all into one model. You saw the model that we did on the cell phone examples. We had we not only had a trend, but we also had seasonality. So everything can be combined into these models. Is a regression model going to be any good? Well, what it's going to really depend on is going to be whether or not we have enough data we have enough data here to actually help us with the statistical side of it. We need to have enough data. And the other thing is you need to be able to identify the variables that are going to be the most effective. Say, for example, if I want to figure out what your exam score is going to be, so this is your exam score up here. If I want to figure out what your exam score is going to be, I can base that on how many hours you study. Is that the best thing to look at? Or is there something else I should look at? Maybe I should be looking at how many hours sleep you got the night before. Or maybe I should A better predictor may be your actual GPA, or a better predictor is to get you to take an IQ test, and that may be a better predictor. So we need to find the independent variables that actually provide the best forecasting model, and we need to have enough data. But given that, this method is very flexible. All right, let's move on. How can we determine the best forecasting model to use? Let's have a look. Well, the first step is always to do a visual graph inspection to see if there's trends, seasonality, to try and pick out patterns in the data. If you want to set up a causal model, you only want to include variables that actually cause the change in the dependent variable. And so basically just use common sense when you're doing that. If a relationship seems random, you may just decide to exclude it. If something just doesn't make sense, even though statistically it does, you may just decide to include it. Often you have to explain that to people, why you're including something that seems totally random. And it's up to you which direction you move in on that, and as far as that goes. So determining the best forecasting model to use, moving on with that. If you've got enough data, if you're in that great position where you've got enough data, you can split your data into the older training data and the newer validation data sets. And basically you can figure out a model based on one set of data and the other set of data you use to actually validate that model. You can also choose a forecasting method that minimizes errors. That's obviously the best thing to do. And a lot of people use the mean square error as the way that they're going to actually measure the error. So depending which one you use, you can use any one you choose, you decide you want to use. But make sure that you're minimizing errors. Fortunately, there's a lot of software packages out there that actually will do all the work for you. They will actually minimize the errors for you. And don't be afraid to use your own knowledge.